Hello there, welcome to this feedback video. Make sure that you correct your work fully. Any question that you go wrong, any question that you missed, make sure that you indeed do it properly. Okay, now the first question we're talking about a circuit here. So what we are looking for is we're looking at this, what we're looking at is a series circuit because we have one loop, okay, so we can see the one loop, okay, so this is here is a series circuit, okay, and we got this one here connected to this one here. Now we need to know the rules for series circuit. So series circuit, the rules. Now for a series circuit, we know that the voltage, they are split. Okay. However, we know that the current is the same, and this will help us in this particular case. Now, calculate the voltage across the thermistor, which is this one here. Okay, now since we know the voltage is split, we know that the total voltage is 1.5 and 0.91 is taken by this one. So therefore, this is, we'll get, how much will this one be? So this is the total. That's how much we have on the other side. Okay, how much is this one? So all we need to do is just take away, and this will give us our answer. And here we go. 2 marks, 2 easy marks. Now we need to work out, state the formula linking voltage, current, and resistance. Now the good thing with this one is this equation is pretty much in order. So voltage is equal to current multiplied by resistance. This is done for us exactly. Now we need to work out the resistance of the resistor. Okay, so now we know that this here is 0.59. So V is equal to IR. Work out the resistance. I need to rearrange it. So V divided by R is equal to resistance. Now V, we just work this out. It is 0.59 divided by current. We know current is this much. So current, we need to convert this into, so 6 times 6.2 times 10 to the power minus 3. So we need to convert this. So therefore, 2, 3. And then this one here, I'll just plug this as it is in the calculator, and I'll get an answer of roughly 2 ohms, and this here will be my answer. Okay, you can see here how easily it is to get those marks. If you got this wrong, make sure that you do this properly. So 1, 2, and 3. Here we go. Okay, now describe the relationship between the temperature and thermometer. So temperature is inversely proportional to resistance of thermistor. Okay, so the word relationship and then it's 2 marks, therefore I need to say it is inversely proportional, and here we go. That's it, that's all I have to say to get my full marks. Now explain how the reading of the voltmeter changes when the temperature of the room decreases. Now it's 3 marks. Let's take a look what happened. Okay, the temperature is decreasing. Now as the temperature decreases, as the temperature gets colder and colder, look what happened to the temperature, what happened to the resistance. The resistance gets very high. Okay, now let's go back to the diagram because we need to understand what is going on here. Okay, now let me delete this. Okay, now the resistance of this guy increases. Okay, now if the resistance increases, if this resistance increases, then we know that the voltage will also increase. It means this guy will take more portion. Now before it was taking how much? 0.59. Now it's going to take more. So if this takes more, we know that the voltage is split. So if this is taking more, that means this one here has to go down. That's how it works because the voltage is split. And that's what we're going to word this in properly. That's how we're going to word this in. Okay, so first of all, okay, so since temperature is decreasing, it means resistance of the thermostat, or the thermostat, what happened to it? The resistance of the thermostat is going to increases. Now I need to know which resistance I'm talking about, because there are two stuff here. There's one for the thermistor and there's one for the resistance. Okay, so this goes up. Okay, so if this goes up, what's going to happen? If this goes up, what is going to happen? Okay, so the thermostat increases, thus voltmeter reading decreases. Okay, okay, so here we go. Okay, so first of all, when temperature decreases, the resistance of the thermometer increases. When this increases, this will cause the voltage shared across the thermistor to increase, and therefore this causes the less voltage through the resistor, decreasing the reading in the voltmeter. That's how we are going to get our marks. Now this one here is straightforward, because what we've done is the scientist is measuring the count rate. Okay, now how can we account for the background radiation? So we know we have background coming up. So let's say we have the source. Now we get stuff from the source as well as from the background. Now what's happening is this person here is measuring the count rate from the radioactive isotope, but it's also getting everything as well. So we need to talk about this one here. I think you guys already know this one. So it's 1 mark, which is a shame. Normally this would be worth like 3 or 4 marks before. Okay, so you need to remove the isotope and measure only the count rate from background. And finally, you need to subtract. Okay, so now that we've removed the isotope and we've got reading from the background, so now we can subtract the background count rate from the isotope. That's what we need to do pretty much. That's will give you a 1 mark there. I know you can even break it down into 3 points, but unfortunately, so it's up to you if you want to keep it safe. But this will give you only 1 mark, unfortunately. Now this one here is 2 marks. What is meant by half-life? Now half-life, it tells you there's half-life. Okay, so half-life, it is the time taken. This will give you 1 mark. So time taken. Okay, for half of the radioactive isotope to decay. How long will it take for half of that isotope to decay? That's how much it is. That's how it is. So here, for example, if you set at 50, how long will it take? So in this case, so from 50 to 25. So how long will it take for 25, for half of that, for half of the 50, for half of the isotope to decay? That's what is half-life. So you get 1 mark for saying half decay, for saying time taken, and the other mark you get for mentioning these two here. Okay, and now we need to use the graph to determine the isotope. Now it's 2 marks. Okay, Now we start with 50, that's the original one. Now half of 50 is 25, so this here is 25. So I go across at this point and then I go down slowly. Okay, and that's how much I get. So I get something here. Now this one here is 3, so therefore I get 2. So 2, 4, 6. Okay, now I need to be sure whether this is indeed correct. Okay, so you can do half of 25, which is 12. So that's 15. So yeah, 15 is here. That's 2. So somewhere here, goes there, goes down. Okay, so it tells you how much it is going to be in this case as well. Okay, and this is 0 0.6. 0.6. Okay, now I can also clarify for some other points as well. Okay, now if this were 3 marks, if this question were 3 marks, then I will have to find another data as well on it. So here I got 1 point here, which is enough for 2 marks. Okay, if this were 3 marks, I need to go down again. So half this again to go across and so on. Okay, so if it's only, I'll add the second dotted line only if it's 3 marks, but 2 marks, that's fine. All right, let's move on. Now this question here should be straightforward. Now by similarity here, we're talking about other similarity. Now we know that it is an electromagnetic wave, so all electromagnetic waves, gamma rays, X-rays, visible light, all these. So we know these are transverse wave. Transverse wave that goes speed of light. Okay, they can travel through vacuum. So all these things they can do. Now similarity, I'll just put transverse waves. Okay, they travel the speed of light. They can also go through vacuum. Now they have different frequencies. This frequency is different. It means they're gonna have different wavelength. Okay, so if you remember when we talk about the EM spectrum way back in year 9, then if frequency is different, then wavelength will be different as well. Now equation, again, the good thing is they were listed it properly. So speed is equal to frequency multiplied by wavelength. Okay, here we go. Now we've got 2 marks and we need to work out the wavelength. All we need to do is rearrange it. So wavelength is equal to speed divided by frequency. Now the speed we know, everything we know. So I'll just plug this into my calculator as it is. I will not change anything. Just put it in my calculator. I'll make sure to use bracket because some calculator are not good at bit mass or the bud mass thing. So make sure that your calculator is, you put your bracket there just to be safe. So 0.058. So this here is my answer. There we go. And finally, we'll just talk about this. So this here is transverse. Okay, so you look how easily you can get to marks here. So 1, 2, 3, 4, 5, 6. 6 mark easily here. Okay. Good. Now, whenever we have to describe the difference, we are talking about just define them. So transverse, oscillations are perpendicular to direction of energy transfer. Longitudinal, again, oscillations are parallel to direction of energy transfer. Here we go. Now, there are a few things we need to be careful with. I'll underline it for you in red. So I need to see the word oscillations there, perpendicular direction, oscillation per parallel direction. So make sure that we are talking about the right thing. Now, if you've drawn it properly, that's fine. Okay. However, we need to make sure that this one is drawn properly. That's the one that we tend to struggle with, tend to forget about. But if you just remember the definitions and just define them, then you should get your 2 marks there. Look how easy it is, just memorize them. Okay, so if you've got this wrong, make sure that it is indeed done properly. Okay, before we move on. Now we're talking about our nebula. Nebula is very straightforward. Now let's take a look how far we are. Okay, yeah, we're nearly done. Okay, we're nearly done, so no problem at all. Let's do this quickly and efficiently as possible. Okay, nebula. Now, how do we get from a nebula to a star? Okay, now we know we have a nebula, and then we have a protostar, and then we have a main sequence. Okay, now what is a nebula? That's the first thing we need to talk about. So nebula is a cloud of gas and dust. That's what we need to talk about. That's the first point. Okay. Our second point is gravity. Okay. Causes the nebula to collapse. Okay, so by collapse means it's going to bring all these together. Okay. Third point is as the gas and dust get close together, the temperature goes up. So it gets hot and starts to glow. Okay. Okay. A protostar is formed. Protostar is formed. Okay. Okay, protostar is formed, and what's going to happen is then it's going to get more hot. Temperature's going to keep going, so gravity is keep pushing them together. Okay, and then finally, when fusion starts, gravity and outward pressures balance. Okay, then we have reached a main sequence. Okay, so what I've done here is I've gone a little bit beyond the 3 marks, but if you talk about any of these points, then you should be getting your marks there. Okay, and now how do we go from a main sequence to a neutron dwarf star? So if you remember, we've got nebula, protostar. Now if you put the flowchart, you would not get marks. The flowchart does not tell us, does not describe what's happening. The flowchart just tells us what's in the next step. Okay, just tell us what's the next step. It doesn't tell us what is going on. So I'll just put it there for you to see what is going on. So after a main sequence, if the star is like our sun, then it's gonna go into a red giant. Okay, after red giant, it's gonna go into a planetary nebula, and then it's gonna go into our white dwarf. Now we need to talk about these steps here. Now, first of all, how will it go from main sequence to red giant? So, for this to happen, hydrogen, okay, runs out. So that's what happened. Hydrogen runs out. Okay. So next, what's going to happen is the core of the star collapses. Okay. Collapses, and outer layer expands. Okay. This forms a red giant. Okay, now red giant is going to fuse. It's going to fuse helium now. It's going to start fusing helium. Okay, so started fusing helium. Okay, fusion of helium. Okay, as you can see here, there's a flow to my description. Okay, and what's going to happen next? So when helium fusion stops, okay, the outer layer is given off as a planetary nebula core. And what happens is the core collapses again. So core collapses, core collapses, and becomes the white dwarf. Okay, and this, we don't need this, so I'll delete this for now. So any 4 of these points here. So I've done went a little bit beyond, so we understand truly what's going on. Okay. Now this one here should be straightforward. Efficiency. What's happening to efficiency? Now first of all, I will put the equation down. So efficiency is equal to useful over total. So 50% means 50% of the total energy put is transferred usefully. Here we go. That's all we need to say. So you need to say that it's so 50% of how much we're putting in, the total energy we put in, only 15% is used properly. Only 15% is used usefully. Only 50% we can use it. The rest is gone. We can't use the rest. It's dissipated somewhere. Now, work out the total energy. I need to rearrange this for efficiency. Now, useful, it is 6. Now, the reason why I leave it in 6 because look at the units here. It is in K. Now, efficiency for what? Efficiency for the small hydro. Look at the graph. Here we go. Small. So go all the way to here. And this is 90%. 90%. So 90% is 0.9. So therefore, this here is 6 divided by 0.9 is 6.666, which is 0.7. 0.7. Now to get my full marks here, I need to say 0.7 because the answer is to 1 decimal point. Otherwise, I will not get my mark. Okay, now this one should be straightforward. In the nuclear reactor, the fuel is indeed uranium. Okay, now this is fission. This is fission when you split things. Okay, if you remember, if I draw this here, we got the neutron. It gets fired into our unstable nucleus. Our unstable nucleus gets more unstable and then splits into smaller daughter nuclei, and then we have neutrons being given off. So therefore, nucleus absorb a neutron, split because it is unstable, split into 2 daughter, called daughter, release 3 or 2 neutrons. So these are neutrons. Neutrons. Energy is transferred into energy of fission. So what's happening? These guys are moving very, very fast. So it's transferred into kinetic energy because they're moving very fast. There we go. This one should be straightforward. How can we calculate the acceleration? Is the gradient. Gradient is change in y over change in x. So which is final velocity take away initial velocity over time. Now we start. Where do we start? We start at this point. We go all the way to this point here. This is 0. So this here is my change in y, and this here is my change in x. So therefore we go from 4.2 to 0. So therefore final is 0, take away 4.2 divided by how much is this one here? This one is 0. 0. And we get minus. Here we go. So I need to see 1, 2, 3, and 4 the answers. Okay, distance, it is straightforward. It is the area of graph. The area of the graph is a triangle. Therefore, it is area of the triangle's half base times height. Base we know, so base is this here. It is 0.45 times height. We know height already. Height is, this is the height. So 4.2, therefore we get an answer of 0.95 meters. Okay, that's where people forgot. So we forgot that's how to work out the distance from the graph, forgot the equation. Okay, 3. I need to see these multiple steps because we need to make sure that we get this right, especially for next year. Okay, now the object is falling. What is the force that makes things fall? It is, so weight. If you say gravity, gravity is on the force. And what is the force that goes against you? So this is air resistance. Okay, air resistance because there's air, because you're falling. Yes, you're falling through air. Okay, and now we need to draw the arrows. Just draw the arrows. So weight is always down, so from the object all the way down, that's weight. Air resistance always against you, so therefore it's going to be from the object against you. Now this here, this one has to be longer. This one here has to be shorter because we are falling. Because we are falling, so it means the weight has to be more if you want to fall. Okay, so you get your marks for drawing the arrows, just the arrows. You don't need to label them at all. So you get 1 mark for having the correct arrow facing the correct way. A second mark for it originating from the body. So if it does not touch the body, then you lose mark. You need to be touching the body here. So look, it goes from the body, and lastly you get your mark for the weight arrow being longer than the other arrow. Okay, and we are here in this one here. Now here we talk about what's happening for forces. Why is A straight, why is B is curving, and so on and whatnot. Okay, now so from A to B, what is happening? The object accelerates. Now why does the object accelerate? The object accelerates because weight is greater than air resistance. That's why we fall. Okay, now at B, okay, it starts to decelerate. Why is that? Because air resistance increases as speed increases, because what's happening is as we are falling, so from A to B, it accelerates, yes. So when it's accelerating, it means it is going at a greater speed. And what's happening over time is over time there's more air, and the air will cause you to slow down. That's what's happening. The more so if you go at a higher speed, then there's more chance of air coming up and start to decelerate you. Okay, and from C to D, what's happening is we have the weight. Sorry, we have air resistance equals to weight. Okay, so there's no resultant force. So if there's no resultant force, it means there's no acceleration. No acceleration means we have reached terminal velocity slash constant velocity. Okay, that's is the stuff we need to talk about in this particular case to get your 4 marks. Let's keep going. Now we have this here, we're calling the water, blah blah blah. This is the curve. Okay, start from this point, we go all the way down. Okay, now we need to draw a tangent. It tells us here, draw a tangent and work out what we need. So degrees Celsius slash, so gradient. That's what we need to do at 70. Okay, let's work out what 70 is. 70 is here. So go across, so that's where we need to draw the tangent. The tangent will be a straight line, so a straight line I need to see. Okay, unfortunately I don't have a ruler, but you should see something like tangent. Oops. Yeah, it's very hard to do it without. Tangent, straight line. Here we go, straight line. I need to see the tangent. Tangent, and then I need to work out the gradient of this tangent, so therefore I need to see the triangle. Okay, so here my triangle for the tangent. So this here is the tangent. And I need to see the triangles to work this out. So therefore, it's going to go all the way. So carry this on. Again, use your ruler because I can't use a ruler here. Okay, so I need to do what I need to do. So I'll make this as big as possible. So from here all the way. I'll keep on going, keep on going, keep on going, keep on going. Keep on going. Again, use a ruler so this way you do the tangent properly. So okay. So my change one would be I'll use a big triangle here then. Will I use a big triangle or not? Nah. Because this one here just goes away. Again, it's very hard to draw this properly. So alright, so what I've done is I've tried to draw my tangent properly. Okay, so what I'm going to do is I'm going to use my triangle. So from here all the way down, so this will be my triangle here, from here down here across. So this here will be my big triangle. Okay, so therefore I have my change in y and I have my change in x. Okay, so from 57 to 8, so this one here from 0 to 6. Okay, so therefore I have my values. So it's going to be here we go. Now your values will change depending on the way you've drawn your tangent. Now, however, you should be getting a negative value. You should be getting negative because it is the gradient is going in the negative, so you need to have a negative there. Okay, so for you to get your full marks, you need to draw the tangent, you need to try to work out your gradient, and then the negative value should be indeed be there. Now this one here should be straightforward. It's going to be start from 82, okay, and we should be getting a curve as well. So what I'll do is I'll change the pen color to a say red in this case. So 82, we're going to start at the same point. Okay, however, it's going to be a similar curve, but it's going to be above it. So it's going to be something like this. Okay, something, again, it had to be a curve, same point. There we go. That's how it is. So question B. So this here is B. There we go. So this here is B. And that's all you need to do for the question. You need to be a curve indeed. You need to be a curve and need to be similar to the black one. Okay, here we go. Now we are back to this question. Okay, now we have static electricity. Now remember static electricity, how can we do this? Now the question here, this one here is positively charged. Now what's happening is once the handle is turned on, it becomes positive. So if it becomes positive, what's happening to the electrons? Now remember, so only electron can move. So electrons are the only one that can move because if you draw the atoms, so we got the nucleus here in the center and then the electrons orbit around it. So which one is easy to move? Of course, it has to be the electrons. That's why the electrons are the only one that moves. Now, why is this becoming positive? Why is that? It's because, okay, because electrons move away from the dome. That's it. The dome loses electrons, therefore it becomes positively charged because electrons, they are negatively charged. Therefore, that's what happens pretty much. Good, that's it. Now, this one here, we need to remember the equation of energy is equal to I/V/T. Now, we are looking for the charge in this particular case. So, what do we do? Okay, what do we do? What do we do? Sorry, we're looking for current, my bad. So the mean charging current. Okay, current and amps. So we're looking for current. So we need to rearrange this equation. So E is equal to VT. Now energy we know it is here. So plug this in 0.5. Voltage we know it is 120 kilo. So I need to put those zeros. Okay, time is 15 seconds. And no, therefore, all divided by that, I should get an answer of 2.8 times 10 to the power minus 7. So this is the one I will write down. Okay, so this is the value my calculator gave me. I'm not doing anything to it. This is the one I will indeed write down. Okay, let's move to the next one. Now, the handles is turned. Now we place a thin piece of metal. Now the metal here is moving away. So this guy here is moving away. Now the dome, we know the dome is positive. Now how can this here be moving away? So if this is moving away, it means it's getting repelled. Okay, so for it to get repelled, it means it has to have the same charge. It has to have the same charge. This also has to be positive, otherwise it will not be repelled. So that's how we need to talk about. So therefore we need to talk about this one here. Okay, now remember earlier when the dome loses electrons, so here we go, so the dome here is losing electrons, therefore become positive. That's how this will happen as well. So the metal case loses the metal case loses electrons. Okay, lose electrons. Okay, so metal case and metal dome have the same charge. Okay, so if they have the same charge will repel each other. Here we go. That's it. That's it. By losing the electrons, this become positive. Therefore, they become the same charge, so positive here. Okay, because they're losing electrons, so therefore there's less electron, they become positive. Therefore, they are going to repel each other. So this is what we need to see to get your full 3 marks. Okay, this one here, why does the metal case reaches a maximum height above the dome? Now this one here is going to be a little bit tricky. Okay, so what I will do, I'll show you the masking for this one, and then so it's 4 marks. You need to pick any of those 4 marks. 4 points. Okay, so here we go. So this is the mask scheme. The mask scheme is saying here the repulsive force from the dome decreases as separation increases. Okay, name the force. So the weight is down, air resistance up. Okay, slows down, kinetic energy decreases, or gravitational potential energy increases, and so on. Okay, so these are the 4. Any of those 4 points will give you a mark. Okay, so leave this there so you can pause the video and so on. Right, let's move on. Now we have this one here. What is a safety precaution? This one should be straightforward. So goggles. It's not Google, so goggles. Goggles slash tongs to handle it slash gloves. Okay, these are the main ones that we need to do. Okay, now this one here we need to know the equations. So the equation for this one is energy is equal to specific capacity. Now by the water. So water, this is the water, this is the water, and this is the water. All we need to do is just plug this in. Now this is in grams, so we need this in kilograms, so it's going to be 0. There we go. Specific capacity is this much times the change in temperature is 5. If we plug this into our calculator, let's see how much do we get. So we get, and this is about 3,000. That's how we show it. Okay, now we need to work out the temperature difference, change in temperature. Again, same equation. This time we're looking for change in the temperature, so rearrange the equation. Okay, this time for the nail. So use a different color for the nail so you know. So let's use green for nails. This is the nails one. This is the nails one. So energy for the nails one. Now, what's happening is energy is transferred, so the same amount of energy will be used. So 289 will be used. The mass is going to be in kilograms. 1, 2. There should be another 0 there. Okay, times divided by. Okay, make sure it's properly done. Look at where the dot is. So 28 divided by the mass and specific capacity. This will give me 13.7 degrees. Yes, it indeed. The temperature change is very, very, very big. Okay, look how big the temperature change is. Okay, it's massive. Over 1,000 degrees change. Okay, now give a reason why the calculated temperature is lower than the actual temperature. Now, if you go back to the diagram here, the nailed, so pretty much, so heat this up and place this in here. Okay, place it in here, the water. Now what's going to happen is the water will get heated up, of course, but the energy will also be going into the wall of the beaker and then finally into the air around it. So what's happening, I was going to say is we're going to say we have energy lost to the surroundings. So surroundings. So let me just write this properly so you can see. Surroundings, and that's it. That's your 1 mark. Okay. Now, any question that asks you to calculate it properly, I need to see the equation exactly as you see in the video. That's how exactly you need to have it down, because you need to know these things, how to get this done. Okay, so hopefully this will help you understand it properly. Feel free to skip any through it. Make sure that once you're done, you do the feedback sheet given.